Hi everyone, how are you all? Please let me know if I'm audible. Sorry for little delay. Okay, so I guess I'm audible, right? Cool. Let's get started. Happy Republic Day, everyone. Happy Basant Panchami also. So, how was today? Have you celebrated these two festivals? Let me know. And how is your preparation going on? That's most important. Hello, Sri Ram. Hi, Vijay. Hello, Namika. Hi, Kundan. Okay. So let's get started. So today we are mostly going to discuss problems which are related to stack and queue. And let me just tell you that whatever we are going to discuss today is going to be very interesting. Reason being is that we are going to talk about some very good questions. Okay. So let's just get started. Yeah, just give me a second. Just give me a second. This is having some problem. Okay. Okay. So I think it is fine now. Cool. Let's start. So how are you everyone? I hope everyone is doing good. How's your preparation going on? That's most important question that I wanted to ask. Let me know how's your preparation going on. Okay. So hello Akash. Hi Dangerous Kladi. I forgot your name. What's your name? Cool. Hello Satyam. Cool. Let's get started. Today we are going to talk about PYQs based on stack and queue and linked list also, right? So PYQ is based on this topic and linked list. Linked list. So these two topics we are going to discuss, right? So this is data structures marathon. Now, before I go further, let me just tell you that we already have playlist for algorithms. You just need to watch that playlist. I mean, most of the things are covered, especially related to graph algorithms. Let me know if you people have gone through this playlist. This is really a nice playlist. Just a 30 minutes lecture, just 30 minutes lectures. So if you just go through this playlist, then you will get to understand many things. So I will just say that go through this playlist once, and then you will get to understand many things. Okay. So this is the playlist that I will recommend if you want to watch algorithms. Cool. Let's get started. Just give me a second. Okay. Sorry about it. Like this is misbehaving a little bit. Yeah, but I think now it is fine. Cool. Okay, so you can watch this playlist. Like this is very nice playlist that I have created just for the graph algorithms. In the graph algorithms, you have DFS, you have BFS, right? This DFS, BFS, these things are there, and also the spanning tree, digestra. So I've talked about the spanning tree. I've talked about the digestra. I've talked about most of the graph algorithms that we have in our syllabus. So this is very nice playlist. Let me know if anyone of you have watched these playlists. Okay, schema is saying that sir, please take programming type questions related to stack and queue. Actually, I have just taken only the PYQs. If in the PYQs there's a programming question is there, then I have taken it. Otherwise, like I have not taken it. So any good PYQ, I will not skip. That's my promise. Okay. So if you talk about the PYQ, we are not going to skip the PYQ. That's what I can definitely guarantee. Any good PYQ. So before that, let me just tell you that we are all set for All India Mock Test 3, and this test is just designed to make you be ready for the gate. Okay, so be gate ready with this our final mock. I will highly recommend that you just attempt this test on 29th of January at 9:30 a.m. This test is going to be the I mean, the most I cannot predict the gate paper, but I can say the most accurate mock test that we can make for the agent mock test for the gate 2023. That's going to be this AIMT3. So just attempt this test and you will definitely enjoy this test, just like other AIMTs that you must have enjoyed, right? Okay. So let's just get started. So we are going to solve some stack, queue and linked list questions, which are really nice questions we are going to solve. But before that, there are 2-3 questions which are good, and I have not taken in the previous slides, maybe because I was not having those questions in my slide, and these are the latest questions. So latest 2022 questions I have not solved earlier. So let's just start with this particular question. Okay. Okay, Vijay is saying that please bring TOC marathon. I'm not sure that we can bring the complete TOC, but definitely Deepak is planning for the decidability. Yeah, thank you, Kundan. Kundan is saying the DFS, BFS was explained very well. Yeah, thank you. Okay, thank you, Akash. Thank you so much. So let's just get started. What this is saying, that suppose a binary search tree with 1,000 distinct elements is a complete binary tree. What does this mean to say complete binary tree? It means that the all labels are full. All labels are full except last one. I mean, last may be full, may not be full, except last one, right? All labels are full except last one. So this is what complete binary tree means. I mean, last may be full, last may not be full. So I hope you know what does this complete binary tree. Let me know, is this complete binary tree? Yes. Is this complete binary tree? Yes. Is this complete binary tree? Yes. Is this complete binary tree? No. I mean, last label is basically filled from left to right, right? Left to right. This is how last label is filled. That's what complete binary tree is, right? Okay. Left to right. Cool. Now, what they are saying, that they have 1,000 distinct elements. That's cool. And with this 1,000 distinct elements, they want to make a complete binary tree. Okay. Then they are asking that where does the third largest element is stored, right? The tree is stored using the array representation, just like of binary heaps. Okay. Array representation of binary heap trees, it means just like a binary heap representation, just like a heap we represent just like this, we are representing this binary search tree also. Assuming that array indices start from 0, then where does this third largest belong to? That's what they are asking the question. Okay, let's just see. So if you are having 10, how much element? 10, okay, 1,000 element, 1000, right? So which means if you are having 1,000 distinct elements, then let's just see whether this distinct will matter to us or not. But let's just solve this question with the given data, then we will see if there is any variation possible. Then let's just see that if it is complete binary tree, then how many labels are possible, right? How many labels are possible? Something like this. If it is complete binary tree, so what we are going to do, we are going to take this node, one of the root node, and then we are going to say that if we want to make a complete binary tree with 1,000 nodes, then I think if you have, let's suppose 2 power 10, which is 2 power 10 minus 1, if you have 1023 nodes, then you can fill all the levels, right? You can fill all the levels up to maybe level 9 or level 10, right? So if you have 1023 nodes, then you can fill all the levels. But since you have just 1,000 nodes, then can you fill all the levels? Then definitely not, right? So what we are going to do, we are going to make a binary search tree, but all the levels might not be full. So basically, I mean, till the second last level, it will be full, right? Because till the second last level, if the last level, I mean, let's just say this is level 0, this is level 1, okay, this is level 2, then if I say that this is 1023 nodes, then I think this is 2 power d plus 1 minus 1. So this is 2 power 9 plus 1 minus 1, which is basically you have till 9 levels, right? Or 10 levels if the leveling start from 1. So I hope that is fine. Like I'm assuming that this particular computation is fine, that we can find out that till there are 9 levels or 10 levels, right? So let me know if this particular computation is fine. Cool. Now, if there, let's suppose 9 levels or the 10 levels, if the level is starting from 1 or 0, does not matter. So let's suppose I'm starting from 0. Then the last level, which is the 9th level, they are saying it is not filled completely, right? This ninth level is not filled completely. That's what they are saying. Now they are saying that you are like, it is not necessary that ninth level is filled completely, because the nodes are 1023 only. Oh, sorry, 1000 only. But the second last level must be completely filled, right? The second last level, whatever it is, it must be filled. But the last level will not be completely filled. That's what I can argue from here. So basically, okay, let's suppose the level is starting from 1 or 0, does not matter. Let's not worry about it. Let's say this is last level. This last level may not be completely filled. I mean, here the some portion is empty. In the last level, this portion is empty. But the second last level, I can say this is completely filled. This is definitely completely filled, right? So let me know if this is understood to everyone. The second last level, till second last level, how many entries you have? Till second last level, you have maybe, if it is 2 power 10 minus 1, then it must be 2 power 9 minus 1, which means it is 5 1 1. So till this level you have 5 1 1 nodes. So these are the 5 1 1 nodes. These are the 5 1 1 nodes, right? And then you are saying these are the 5 1 1 nodes. Then the remaining nodes, which is 1000 minus 5 1 1, are at the leaf, which is whatever it is. Let's not worry about it. Whatever it is, these nodes are at leaf, right? So these nodes are at leaf, and then because the total nodes are lesser than 1023, that's why last level is basically not completely filled. The interesting point here is that all levels are completely filled. That's what important. Okay, all levels are completely filled. Let me know if you have understood this particular scenario, that about what I'm talking about. So basically all levels are completely filled, but the last level is not completely filled. That's what they're saying. Cool. Now let's just do one thing. Let's just extend this idea, and let's just try to understand that where does the maximum I'm storing, right? Or maybe before that I can talk about, instead of talking about the maximum directly, maybe I can talk about some more interpretation of this particular binary search tree. So as I'm saying, the last level is not completely filled. Now suppose if it is 1023 nodes, then what will happen? Then the last level must be completely filled, right? Then the last level is also completely filled. Cool, great. Now let me ask you something. Suppose it is not 1023, it is just 1022 nodes. If it is 1022 nodes, then what's going to happen? You will say that only the last one node, this node is not there, but this node is there, right? If this is 1022 nodes, then only one node is not there, right? Only one node is not there. This is what you will say. Only one node is not there, right? If it is 1022 nodes. Let me ask you another question. Let's suppose it is 1021 nodes. It is 1021 nodes. Then what you will say? If it is 1021 nodes, then you will say that, see, suppose it is 1021 nodes. Then you will say that these two nodes are not there apart from only two nodes, right? See, anyway, this till this point I'm already filled, right? Till this point I'm already occupied. I'm only talking about the last level, right? I'm only concerned about the last level. So what I'm saying, if you have 1021 nodes, then only two nodes you do not have. Otherwise all the nodes you have, actually, right? All the nodes you have. Only these two nodes you do not have. This is what we are saying. Let me know if that is understood to everyone, right? So I hope that is clear. Cool. Now let's just understand it more carefully. So this question has been asked in GATE 2022. So let's just understand this more carefully, that what they are saying. Now they are saying 1000 testing nodes are there. So if there are 1000 testing nodes, like I'm 100% sure that this particular node, okay, this particular node, whatever it is, like, I mean, this is basically the last node, or I can say the rightmost node of second last level, right? I can say this is the last rightmost node of the second last level. If there are 10 maybe 1020 nodes, right? If there are 1020 nodes, let's suppose, then this is not having children. This is I'm sure. Actually, I will tell you that why I'm only worrying about this particular node, because the question is asking something which makes me worry about only this particular node, whether it is having children or not. Let me know if you are having 1023 nodes, then whether it will be having children or not. Answer is yes, it will be having children. If you are having, let's suppose, if you are having 1022 nodes, then it will be having just one child. If you are having 1021 nodes, then it will not be having any child, right? Everyone else will be having child. Let's suppose if you are having 1020 nodes, then it will not be having child. Similarly, it will not be having child, something like this, right? So if I just say that the total number of nodes that you have is basically 1000 only, then let me know if this particular node is having child or not. That's the simple question I'm asking. Then I will just read the question again. So before even I read the question, I just want to ask you that whether this rightmost node on the second last level, whichever it is, right, is this having any child or not? If there are 1000 nodes that you have, if there are 1000 nodes, then in this case, let me know what is your answer. Okay. So I hope you are convinced that this is not having any child, right? Or because you are just having you are not having enough number of nodes. So I hope that is clear. Okay, now let's read this question again. What they are saying, let's do one thing. Let's just forget, like whatever I just told you, let's just forget about it and let's just read this question again. What they are saying, they are saying, suppose a binary search tree, okay, you have a binary search tree which is having 1000 distinct elements and also is also a complete binary tree. That's great. Now the tree is stored using the array representation. I mean, there is a complete binary search tree, that's the complete binary tree, okay, and assuming that array indices start from 0, the third largest array index they are asking. They are saying that where does your third largest exist? Let's just see, okay, let's just see where does your third largest exist. Now what I'm saying here is that let's suppose this is the last level, okay, this is the last level and this is second last level, okay. Let's not worry about the numbering whether it is 9th or 10th. Let's say it is second last level. Let me know if this is having any children, if this is having any children. If you are just having 1000 nodes, if you are just having 1000 nodes, then I just told you that you cannot have any children, right? Similarly, this is also not having any children actually, right? Because you are just having 1000 nodes. So I hope that is clear to everyone. Okay, now let's just quickly see that where does your largest lie. Let me know where does your largest lie. Okay, where is your largest? You will say, if you want to find out your largest, then you will, since it is binary search tree, then what you will do, you will go to the right, okay, and then you will go to the right and then rightmost, then you will stop here. Since you know that this is not having any children, that's why you will stop here only. And you are 100% sure that this one is the largest one, because this is not having any children, and that is why this one is the largest one. Let me know if this is clear to everyone. Okay, so let me know if this is clear. So this is the largest one. Now, do you remember, if you just joined the yesterday's class, do you remember I told you the in order projection? Do you remember? Have anyone watched the yesterday's lecture? Let me quickly know if you have watched, and do you remember that what was that in order projection, like the way I have told you that how you can basically manipulate the in order, right? I mean, how you can visualize the in order basically. Okay, so maybe I can have that diagram with me. So I just pasted this diagram. So this is the in order projection that I was talking about earlier, right? So basically, what you need to do, I mean, you can just project the nodes that I yesterday talked about. Okay. Satyam is saying I watched twice. Okay, thank you, Satyam. Yesterday's lecture you watched twice. Thank you so much. Okay, so let's just see if I can do this question. See, now this is the largest, and we know that in order of BST is sorted, right? That's what we already know, that in order of BST is already sorted. So what you can do, if you want to find the largest, if you want to find the second largest, you can just take the in order. Okay, just visualize the in order. Then the second largest must be this, and the third largest must be this, isn't it? See, just visualize the in order, then you will get to know. Otherwise, I will just tell you the logically also. See, I am saying that this is the second largest. Why? Because if you say that, okay, this is not the second largest, maybe the second largest is something else, then you go to the right of it, then only you will finding something larger than that. But that is the largest, right? That is the largest. So that's why this has to be the second largest. If this is not the second largest, someone else is second largest, then you will go to the right of it, right? And then you will see that, okay, what is larger than this? If the larger than this is just the largest, then it has to be second largest. There is no other possibility. Or otherwise, you can visualize the in order projection also. You can say this is largest, and since this is sorted, I mean the BST in order is actually sorted, right? The BST in order is sorted. That's why you can say this is the second largest, and this is the third largest, right? This is the third largest. But let's just do this conceptually also instead of visualizing. So let me know if that is clear, that I am saying that this one is second largest because if this is not the second largest, you go to right of it, and the element which is greater than this is largest only. So this has to be second largest, right? The only element which is greater than this is largest. So this has to be second largest. There is no other possibility, right? So this is the second largest. Now let's just see which is the third largest. So let's suppose I'm more interested because the question is actually asking about the third largest only. So I'm more interested in the third largest. So let's see that what is the third largest, right? Okay. So third largest. Let's see what is the third largest. Sorry, I'm having cough and cold since many days. Okay. So where does the third largest lie? Now what you can do, you can say that okay, that has to be lesser than the second largest. Okay, third largest has to be lesser than second largest, isn't it? Third largest has to be lesser than second largest. Then you will go to left of it. And since there is only one node, that's why you will say that this is the third largest. Otherwise, you can just sketch this to a ground, just like I told you yesterday. And you know that if you sketch that to a ground, then you will get to know that what is the in order, right? So otherwise you just find the lesser than this you will finding on the left of it. Since there is only one node, and we are convinced that it doesn't have any children, it also doesn't have any children, like these two nodes doesn't have any children, right? We are convinced about it. So that's why I will say this is the third largest. So I will say this is second largest, this is largest, and this is third largest, which they are asking for. Let me know if that particular explanation is clear to everyone, or there is any doubt. Okay, so that's cool. Seems like that it is clear to everyone. Okay, so let's just continue. And let's just see what this question is asking. What this question is saying that what is the index? What is the index of the third largest element? Right? What is the index of third largest element? Let's just see. So what do you think? What is the index of this third largest? This okay. This is the third largest. Then you will say the index of it, maybe if this, let's suppose this is the index 1, then that you know that this is 2i plus 1, right? 2i plus 1. This will be 3, and then so on and so forth. So you can find out the index of it. So I think I have the slide with me. Okay. So okay. Maybe do you want to try it quickly? That what is the index of this third largest? Let me know. See what you need to do. Let's assume that that this is having the node which is the root node which is having the index 1. Then what you need to know? You need to basically do 2i plus 1 only, right? So you need to just do 2i plus 1, and then you can find the index of like you can keep on doing right, and then you can find the index of the second largest, which means index of this one. So you can keep on doing right. So which means from 1 to 3 like that. So I have this with me, which means this index is, let's suppose 1, then this index will be 3, then similarly this index will be 7, and then 15. Then based on the label you can find out this is 255, this is 255, which is index of second largest, right? And then they are asking index of third largest. So index of the largest will be 255 into 2 plus 1, right? The index of largest will be 255 into 2 plus 1. Index of third largest will be 255 into 2, which is 510. Okay, so this is the index of the largest, but they are saying that index is starting from 0. Since index is starting from 0, that is why you will say that this is not 510, this is 519, right? So final answer is your 519. 510 if the index starts from 1, but the answer is 519. Let me know if that is clear to everyone, or there is some doubt. Sorry, 509, not 519. I'm sorry about it. So this is 509. Okay, cool. Now let's just do one thing. Let's just see if we can have some more variation of this question. So they have asked the third largest. What do you think? Where does the fourth largest lie? Okay. So let's just see where does the fourth largest lie. So you know largest, second largest, third largest. Then what do you think? Where does the fourth largest lie? Where does it should be? 'See, let's just try if we can actually do this using the in order projection, right? So I want to find out the fourth largest. So let's just see if we can do it using the in order projection. Let's just squash that to a ground. So this is second largest, this is third largest. The fourth largest has to be greater than the third largest. Sorry, this is largest. Okay, first largest, second largest, third largest. Fourth largest has to be lesser than, just lesser than the third largest. So it should be here, but there is nothing here. That's fine. But then what you will say that what is the fourth largest? Anyone wants to try? Yes, Sriram, that is fine. So he is saying the parent of second largest. Why? Because if you just see the in order projection, that how we do the in order projection. Let's suppose this is some node A, okay, or maybe X. This is some node X, and then I have I have on the right hand side I have this is second largest, and this is the whole structure that I have, right? So let's suppose this is the second largest, this is the third largest, this is largest, right? This is the last level that I have. This was the last level. Sorry, this was the second last level actually, right? This was the second last level. Anyway, this is the third last level, and this is the fourth last level. Anyway, doesn't matter. But yeah, if you just squeeze this to a ground, then you will get to know that okay, here the X will come. This is the third largest, this is the second largest, this is the largest, right? So this is the third largest, this is the second largest, this is the largest. So that's how it is sorted. So this X is nothing but the parent of second largest. See this how much this squashing is helping you again and again, right? So that's why, yes, Satyam, that is correct. That's why you will say that this is the parent of second largest. Okay, cool. Let me ask you another question. Suppose they say maybe that uh, if fourth largest position is, or the index is, okay, index or position both are fine, I mean whatever you want to call, index is 126 and index is starting from 0, okay, index is starting from 0, then what could be maximum number of nodes in BST that is represented as complete binary tree. That is complete binary tree, or I mean that's the same question, right? That is complete binary tree. Do you want to try this question as a homework? Do you want to comment it out the answers? Okay, just try this variation. Let me know if you want me to solve this question here, or I think if you just do a proper analysis, then you should be able to solve this question. Try this variation at home and then just comment out your answer, right? And variation at home and just comment out your answer. Let me know if that is fine to everyone, or do you want me to solve it here only? Cool. So I think you can do it, right? Okay, let's just continue. My question is that like if the fourth largest index is given to you, then they are asking what could be the maximum number of nodes in the BST, okay, that can be present. Yeah, I think that is a nice question. That is a very nice question. So this is a little variation that I'm creating. Okay, one of the typical kind of question that you can expect from in the AIMT. That is not from the BST, but yeah, you will see the surprise. Okay, but yeah, some typical these kind of questions I have asked in AIMT also. Cool. Let's just continue. Let's just see this question which has been asking GATE 2022. Now this question is saying that that you have given a hash table or you have given a hash function and they are asking expected number of keys in a slot. Let me know if earlier question is fine, and then only I will move to this question. Is the earlier question fine? You can try this variation at home, and we have done it very nicely, right? I mean, let me know if there is any help you need in visualizing this question. See, in this question, first you need to make sure that okay, till this point everything is full, right? Till this point everything is full. This particular area is full, right? This particular area is full. You cannot change this area. Now you are talking about the last area, right? You are talking about the last level. In the last level, we talked about the things that are needed to talk about. Okay. Let's just continue. What this question is saying, they are saying that suppose we are having n keys, m has table slots, so number of keys are given, number of keys that they want to map is basically n, and similarly number of hash slots, basically number of slots, you can say number of slots are also given, which are basically small m. And two simple uniform hash functions h1 and h2 which are given to you. Suppose our hashing scheme uses h1 for the odd keys and h2 for the even keys, then what is the expected number of keys in the slot, in any slot? Okay, so what they are saying, that you want to map a key to a slot which is given to you. This is the hash table that you have. You want to map this key to this slot, some of the slot. Then what they are saying, that what is the expected number of keys will move to one of the slot, any slot. Let's suppose slot I. They are saying what is the expected number of keys. Expected means the total number of the, I mean the average number of keys. So what is the difference between expectation and average? Can anyone tell me quickly? Expectation versus average. If you are GoClasses student, then you must be knowing it. Okay, let me know if you know this. Can you tell me this in one line? What is the difference between expectation and average? Okay, otherwise I will take a session, don't worry. Okay, I will take a session on probability just tomorrow or maybe day after tomorrow. Cool. So what they're saying, that if you're mapping a key to some slot, then on an average or expected number of keys that are mapping to this particular slot, that's what they're asking. So they have introduced some h1 and h2, but before I go to this h1 and h2, let's just see if I can do this just for the simple uniform hash function. Simple uniform hash function is given to me, hash function. Let's suppose this h is given to me, and let's just find out the expected number of keys, expected number of keys mapped to a slot I. Okay, let's just find out this. Let me know if everyone is with me. Okay, is this okay to everyone, that what we are going to find out? Now what is this uniform hash function? Uniform hash function means that if you map any key, then this key will map to some slot. So let me write it here. So uniform hash function means that the probability that you map a key x, that will go to any random slot. Okay, I, any slot you talk about, maybe 1, maybe 2, any slot. Okay, let me say I. Okay, or maybe 1, 2, whatever you want to call, you want to say here. So any slot you can write here 1, 2, anything. Okay, and then the probability is 1 upon m, which means this is a hash function which doesn't differentiate between the slots, which means this is a hash function which map every key to a equal probability. With the equal probability, it map to every of the slot, right? So that's called the uniform hash function. This is the definition of uniform hash function. Anyway, in simple terms, you can say that it is mapping any key with equal probability to any of the slot, right? Yes, Dangerous Clady. So what is your name? I actually forget. I mean, it is better if I if I take your real name instead of saying Dangerous Clady. You can tell me your real name if that's comfortable. Okay. So let's just see how to solve this question. Now what I'm asking is that if the simple uniform hash function is given, and then they are asking you that what are the on average, how many keys map to some slot. Okay, maybe slot I. So on average, how many keys map to, let's suppose the slot number 1, slot number 2, any slot. Let's suppose this is slot number 1. So I'm asking how many keys are mapping to on average. Okay, on average, there might be many number of keys which are mapping to here. I'm asking how many on average are mapping here. Okay, good. Let's just see if you can solve it. Can you tell me the answer? Can you tell me the answer here? Maybe the answer is GG. Can you tell me directly the answer? If you know this is the load factor, right? I mean 1 upon m is the probability for one of the key. If there are n keys, then it seems like the answer is n upon m, right? Seems like the answer is n upon m. So answer is n upon m definitely, but we will see it little bit I mean mathematically, right? Not just with the intuition. So our intuition is saying, this is our intuition is saying that answer is n upon m. There are n keys, each key is going here with the probability of 1 by m, 1 by m. Then maybe on average, I mean I can give you the example. Let's suppose n is equal to n is equal to 100 and m is 10, which means there are 100 keys and there are 10 slots. If there are 100 keys and 10 slots, then each bucket will be having how many keys? 10 keys, right? Each will be having 10 keys. Each will be having 10 keys. So this is what our intuition is saying, that answer should be n upon m, right? This is what our intuition is saying. But let's just see if we can do it little mathematically also. Okay. So let's just see this. So what I'm saying here is that we want to know the expected number of keys mapped to a slot I. So let's suppose I define a random variable xi, okay, or maybe see what I'm saying here. I don't want to confuse you, so I'm saying slot I. This slot could be anything. I'm fixing my slot. So for example, just for the sake of illustration, what I'm saying here is that let's suppose the slot number is 1. Okay, I don't want to keep it I or j or something. I mean I don't want to keep it variable name. I just want to keep it any slot. So what I'm doing currently, I'm finding out the expected number of keys that map to the slot 1. Now, once you find out the expected number of keys of map to slot 1, you can apply the same method to find out the expected number of keys to the slot 2. Actually, there is nothing specific with this one. You can use the same technique for any of the slot. Okay, I'm just taking the slot 1 to just give you the example. So, expected number of keys that map to the slot 1. This is what I'm interested in finding out. Let's just define a random variable x1, a random variable x2. Similarly, m random variables. If there are n keys, right? So there are n keys. So I'm defining a random variable associated with each key. Okay. So x1 is the random variable that is associated with first key. Okay. Similarly, this is the random variable. This is associated with the second key. Similarly, this is the random variable. This is associated with last key, right? There are n keys and I have defined a random variable x1 which is for first key, x2 which is for second key, like that, right? Now what I'm saying, x1 could either be 1 or it could be 0. Okay, if it is 1, then I'm interpreting, this is my definition of random variable. I can define a random variable of my choice. So what I'm saying, x1 is 1 if first key goes to, okay, or maps to slot I, maps to slot, okay, I'm talking about slot 1, so let's say slot 1. Okay, 0 means first key, it is 0 if first key does not map to slot 1. Similarly, this x2 will be having, see, these are the random variables that I have just defined for each key, right? For each key I'm defining a random variable. Okay, just listen here carefully and then you will get to know like what is happening here. I'm saying these random variables can take values 1 and 0, right? Can take values 1 and 0. Now what I'm saying here is that this can take value 1 if first key maps to slot 1, key maps to slot 1. Okay, there is no expectation or something. I'm just saying that this first key maps to slot 1, then this is taking one value, otherwise it is taking 0 value. This is taking 1 if second key maps to slot 1. Similarly, this is taking 1 if third key maps to slot 1. Okay, cool. Similarly, this will be taking either 1 or 0 depending on if nth key or if last key maps to slot 1. Basically, I'm talking about just slot 1. You can talk about any ith slot in general. Okay. So if I just define a new random variable x, which I just say this is x1 plus x2 plus x3 plus xn, then can you just tell me the meaning of this random variable, this x, in English? Okay, in just plain English, tell me the meaning of this random variable x in the plain English. See, you will say that this x1 is 1 and 0, 1 and 0, like similarly it is taking either value 1 or 0 depending on whether this particular key maps to the slot 1. So if I sum all of this, let's suppose this is 1, this is 0, this is 1, this is 1, this is 0. So what will I get? I will get the total number of keys, the number of keys which are mapping to slot 1, right? So this x is basically representing the number of keys which maps to slot 1, isn't it? I mean, I'm just asking you the English meaning of this x. The way I have defined this x1, x2, x3 should tell you the English meaning of this x, right? Okay. Now what they're asking is that ex. They're asking expectation of x. Okay. See, I don't want to just tell you directly that this is n upon m. I mean, that's not the way we teach it at Go classes. You should be knowing that the complete procedure so that your mind can get open that, okay, this is how the random variables works actually, right? Cool. Now, yes, right? That Dangerous Clady is saying that random variable is a function to a real number. Yeah, so that is that you might be knowing, but that is not important. I mean, to understand at this point in time. That is okay if you know it, right? The definition of random variable is not much important, but what they're asking is that they're asking the expected number of keys, expected number of keys maps to slot 1. This is what they're asking. Let me know if that is clear to everyone. See, they are asking in this question the expected number of keys in a slot, right? This is what they're asking. Cool. Now, basically, we have formulated our problem, right? Very easy to formulate. I mean, once you understand that how we are going to formulate, then it is quite easy to formulate. I will give you some example also that, I mean, using which you can solve you can solve that question using just a similar method. This is not a method just a particular to hashing. This is a general method. Okay, so let me first tell you that how we are going to do it. Then we will give you the more examples also. Let me know if that is clear. So this is how we formulate our problem. Right? This is how we are formulating our problem. Cool. Now what they are asking is ex, which means let me go further. Right? This ex definition is clear. Like, I mean, the way you have defined your x, x1, x2, x3. Now finally you can say they are asking ex, which means they are asking e of x1 plus x2, since x is just x1 plus x2 to xn. Since I can apply linearity of the expectation, which means that I can just move it aside. This is basically applicable for any random variable. Okay, I mean, there is a formula which is something like this. This is applicable for any two random variables, or in general any n random variables. Okay, this is applicable for any random variables x and y. Tell me, is this also applicable for any random variable x and y? Variance of x plus variance of y is equal to variance of x plus variance of y. Is this also applicable for any two random variable x and y? Tell me, is this also applicable? Answer is no. This is only applicable when x and y are independent. In our case also, in although the x1, x2, these are independent because every key is independent to every other key. They are mapping to some slot with 1 by m probability. But I mean, although these are independent, but I don't need independency. This is what I'm saying. From here to here, if I want to go from here to here, I don't need independency. This is true in general. See, this formula is true in general, but this formula of variance, it is not true in general. It needs a condition on the x and y, which is the condition of independency. Okay, cool. Yes, Akash. That is nice. Okay. Now this is what they're asking. I think we can easily do it. So can you calculate the expectation of x1? Expectation of x1 is p into, so if you remember the formula, px, right? I mean, okay, I think the way you write it, x p x equal to k or whatever, right? Or maybe let me just write it in the short way. So x p x, which means the value of x into the probability of it. It takes value 1, and with what probability it will be taking the 1? This is the English thing that I have defined, but can you tell me mathematically the first key maps to slot 1? What is the probability the first key maps to slot 1? See, x1 is taking the value 1 if first key maps to slot 1. This is the English thing that I have defined, but in terms of probability also you can tell me, right? So what is the probability by which x1 is taking value 1? What is the probability? You will say the probability is 1 upon m, because with 1 upon m probability the first key will map to the slot 1, right? Because these are the equal probabilities, and this is 1 minus 1 upon m, right? This is 1 minus 1 upon m. So anyway, so this is the 1 upon m probability. Now if I want to find out the expectation of x1, then you can say 1 into 1 upon m plus 0 into something which is 1 minus 1 upon m, right? Okay, 0 into something. So basically like that. Then 1 upon m is the expectation of x1. Similarly, every random variable is symmetric. I mean, x2 is also like that. So expectation of everyone here is 1 upon m, 1 upon m, 1 upon m. And what they have asked is expectation of ex. So finally, you say just give me a second. Yeah. So basically, they have asked about the expectation of x, which is nothing but 1 upon m plus 1 upon m plus 1 upon m till n times, which is n upon m. And that's what our intuition said at the beginning. Let me know if that is fine to everyone. Let me know if there is any problem. See, we can solve other questions also. I mean, using the same method. If we are having any time confusion, we can solve. We can solve other questions also using the same method. Let me just bring some question using the same method that you can solve. Okay. Some questions that I have given. In the AIMT, I think. Just a second. Let me bring some question. Yeah. Okay. Some simple question. I'm just giving you some simple question that we have asked in discrete mathematics test just for 1 mark. So let me just ask you some simple question. Let's suppose this is the question that I have. What this question is saying? This is saying a graph G is simple undirected graph with 8 vertices. The edges of G are decided by tossing a fair coin. Okay, for each fair coin for each 2 vertex combination. So what they are saying, that whether there will be edge or not, it will be decided by a fair coin, which means you have 8 vertices. There are total 8 C2 edges possible. 8 C2 edges possible, right? But they are saying that for each edge, right? So total edges possible is 8 C2, but for each edge you are tossing a coin, and then you're deciding whether the edge could be present in the graph or not. So edge is added between 2 vertices if and only if head is turned up. The expected number of edges they are asking, right? So 8 C2 is, I think, like 8 into 9 divided by 2, right? Sorry. Okay, what is the formula for NCR? N factorial upon n minus r factorial. And do you multiply by r factorial? If it is n, then I think, if it is c, then I don't think we do it, right? So it is basically 8 factorial upon 8 factorial upon, this will be 6 factorial, which will be 8 into 7. I think you do it. Okay, you do it. So it is 2 factorial, which is 8 into 7 by 2, 8 into 7 by 2, not 9 by 2. Okay, which will be 28. Anyway, so there are 28 total edges that we have, right? Good. So how many edges you have? There are 28 total edges you have, which is 8C2. It is 28, right? So these are the 28 total edges you have, but they are saying that edges could be present there or could not be present there with half probability. So they're asking total number of edges. So let's suppose that x1 is a random variable, which is, I'm saying it is for the edge 1. Okay, this is for the edge 1. x2 is a random variable which is for edge 2. x3 is a random variable. Similarly, x20 is the random variable which is for edge 28. Now what I'm saying that these random variables can take value 0 or 1, right? So suppose I go to the next page. This is taking the value either 1 or 0, depending on if this edge is present. Then it will take the value 1, otherwise it will take the value 0. Similarly, 1 and 0 is 1 and 0, right? Now I define a new random variable x, which is x1 plus x2 till x28. They're asking the expected number of edges in the graph. So basically I will say that if x1 is 1, then edge is present, x2 is 1, then edge is present. So x is basically the number of edges, right? Number of edges in graph. And then what they're asking is that they're asking expectation of x, which means they're asking expected number of edges in the graph. Let me know if that is clear to everyone, right? So it means they are asking this, which is again expected number of edges, which is like this. And since this is equal to e of x1 plus e of x2 till e of x28, which is basically equal to e of x1 is nothing but 1 by 2. Why? Because you will say with 1 by 2 probability it will take 1, with 0 probability, with 1 by 2 probability it will take 0, right? So finally expectation of any random variable here is 1 by 2. So answer is 1 by 2 into 1 by 2 into 28, basically it is 28 times. So on average there are 14 edge present. And our intuition also says same. I mean, if half probability is there for some edge and there are total 28 edges, then you will say on average there are 14 edges present. But I just solved it using a random variable method. Let me know if that is fine, right? I mean, you can define a random variable for each edge. You need to understand that how we are formulating our problem, right? Similarly, here we are defining a random variable. For each key, right? And then they are asking expected number of keys. Then I defined this x, then expected number of keys is something like this, right? So finally, I'm coming up with the n upon m. So anyway, let's just keep this particular thing with us, which is basically n upon m is the expected number of keys that map to any slot. I talked about the slot 1, you can talk about any slot, right? So finally I can say, from here I can say the expected number of keys mapped to any slot is basically n upon m, isn't it? So this is what I can finally say if I'm using uniform hash function, right, for uniform hash function. But now here they are saying that you are using h1 and h2. I mean, there is a hash function h which underlying this use h1 and h2. You are using two uniform hash functions, and h1 you uses for the odd keys and h2 you uses for the even keys. So what they are saying that if there is a key x, if the key is even, if the key is odd, you will be using different hash functions. For this you will be using h1, okay, and for this you will be using h2, something like this, or maybe vice versa, I think. Okay, for h1 for the odd keys, h2 for the even. Anyway, doesn't matter. Okay, so odd even here doesn't matter, but yeah, they are saying h1 for the odd keys and h2 for the even. That's what you are doing. Now they are saying that this is uniform hash function, right? Which means this will map any key to any of the slot with 1 upon m probability, right? So they are saying that this will map to the slot 1 with 1 upon m probability, slot 2 1 upon m probability, slot 3 1 upon m probability. Now what they're asking is that like what are the total number of what are the average number of basically keys that are mapping to any slot, right? Let's suppose this is slot 1, this is slot 1, like that, right? Okay, so what you need to do, you need to understand that what these two hash functions are doing. Let's suppose I say that combinedly this is a hash function h only, right? Which means there is a hash function, and internally whatever you are doing, you are giving to that hash function, and then it is finally mapping. So what you are doing basically, you are picking, since there are even keys and odd keys like that. So basically, let's suppose with the probability p, we pick H1, and with the probability 1 minus P, we pick H2, right? Let me know if at least the problem is fine. Like, I mean, what they're asking in the problem. Let me know. So what I'm interested here is that I want to find out the probability that any key maps to the slot I. I think I made it a little complicated, but anyway, let me just continue. Any key maps to the slot I. This is my hash function. What is the probability that it that maps to the slot I? I mean, with what probability it is mapping to the slot I? That's what I'm interested in. Okay. So let's see if I get something from here. So I will say that okay, with probability P I will picking H1, right? With probability P I will picking H1. If I'm picking H1, then what is the probability? What is the probability? So basically it is just like a conditional thing. I think you know that, right? So probability P, I will picking H1, and okay, this is the P by which I am picking H1 multiplied by, if I pick H1, then what is the probability it maps to the slot I? 1 upon M, right? Plus with probability 1 minus P, I will picking H2. If I pick H2, then what is the probability that it maps to the slot I, which is again 1 upon M, because H1 and H2 are uniform hash function. So if you solve this, you will be getting 1 upon M, which means ultimately my hash function is also uniform, which means this black box, whichever I'm doing, that is actually I'm giving that to I'm giving X to this black box. This is actually mapping to any of the slot with the uniform probability. So let me just simplify this. What we are doing, given this X, we are basically having two cases. We pick H1, right? I mean, it depends whether it's even or odd, right? It depends. But anyway, let's suppose with probability P, I can calculate this probability P, but for now, let's suppose this with probability P, I'm picking H1. With probability 1 minus P, I'm picking H2. I mean, it depends whether it is even or odd, right? Now, what will I do? If I am picking H1, then tell me what is the probability. I just want to know what is the probability that it maps to the slot 1. 1 upon M is the probability that maps to the slot 1. Similarly, here also 1 upon M is the probability that it maps to the slot 1, right? Now, there are other probabilities also, which means 1 upon M is the probability which maps to the slot 2, and 1 upon M is the probability which maps to the slot 3, like that. This is called tree diagram that we have discussed in Go classes probability lectures. Maybe I will take a marathon and I will discuss the tree diagram again. Okay. So basically any node, whatever node in the tree diagram we have, right, the outgoing probabilities are always 1. Outgoing probability, see here, if you sum up the outgoing probability, it is always 1. If you sum up all the outgoing probabilities here, all the slots probability, it will be also 1, right? I will discuss this tree diagram, okay, later, maybe after 2-3 days I will discuss if that is required. And most of the questions from the conditional probability that is dealing with the Bayes theorem, you can solve just using the tree diagram. We discussed very nicely in the Go classes lectures. But anyway, let me just continue here. Yes. So now what I'm asking is that what is the probability that it maps to completely slot 1, right? I'm saying with some probability. If you remember the AIMT question, I mean, many times I have given this explanation. If there are many ways, to come up with some conclusion, right? Maybe from this way, maybe from this way. Then if I just ask you that what is the probability to get this conclusion, you will say sum up of all the probabilities, right? Do you remember the examples that I often give? Maybe let me just quickly give you. Let's suppose there is some place. Let's suppose Jaipur. You start from Jaipur. From this Jaipur, you may go to, let's suppose, either to Hyderabad or to Bangalore. Hyderabad or to Bangalore, right? Let's suppose. And there are some probabilities which is 1 by 3 and 2 by 3, right? And then from this Hyderabad, maybe you go to Indore or you go to Bhopal with some probability. Maybe this time this probability is 1 by 2, 1 by 2. And from this from this Bangalore, you go to Bhopal with some probability, maybe it is 1 by 4. And then you go to some other place, maybe Madras, with some probability which is, let's suppose, 3 by 4. Okay. Suppose these are the probabilities that I have. Now if I ask you what is the probability that you go to Bhopal, what you will say that anything which is coming to the Bhopal, you will sum up all the things, right? Whichever is coming to Bhopal, which means 1 upon 3 into 1 by 2 plus 1 upon 3 into 1 by 2 plus 2 by 3 into 1 by 4. 2 by 3 into 1 by 4, right? So this is the probability that you are going to Bhopal. Let me know if that is clear. Okay. So similarly here also, if there are multiple ways, to come to this slot 1, see here I'm just writing Bhopal once, otherwise that's perfectly fine. If you want, you can write this Bhopal twice also, doesn't matter. You can write this Bhopal here also, and then you can say this is 1 by 4, doesn't matter. I mean, this is the same thing, right? This Bhopal is just I'm writing 2 times. Okay, if you want, you can write the slots 1 time only, doesn't matter actually. Okay, so you can say that with 1 by m probability you are going to slot 1 here, from here also. So what is the probability you are going to the slot 1? That's my question that I'm again and again asking to you. Now tell me, what is the probability that you are mapping any key x to the slot 1? Then you will say the probability is p into 1 upon m plus 1 minus p into 1 upon m, right? With this probability you are mapping any key to the slot 1. That's what I'm interested in, right? Or not just slot 1, that is true for any slot. You can take the slot I, doesn't matter for me. Okay, so if you just calculate it, this is p upon m and p upon m will get cancelled out, then finally you will be just getting 1 upon m, which means that you are mapping any key x to any slot I, maybe 1 or 2, with the probability 1 upon m. That's what I'm finally interested to find out. Let me know if that is clear to everyone. Okay, let me know. So basically this is called conditional probability. I mean, we are essentially doing the conditional probability formula here, but let's not worry about the conditional probability. I mean, let's not worry about the conditional things and how the Bayes theorem is applicable here. But yeah, ultimately this is the Bayes theorem that we are doing. Okay, or not the Bayes theorem exactly, but the total probability theorem, right? So basically if you want to find out any node probability, you need to sum up all the probabilities here. Now this is 1 upon m, which is the probability conditioned on that you already picked h1. Anyway, mathematically I don't want to do it because it may not be required for gate, but intuitively I hope that is fine, right? That all the paths that are leading to this particular node, you can say the probability of happening this particular node is basically this much, right? Something like this, right? Something like this. You can write it once, twice, does not matter. Okay, everything is fine. Okay, now finally you understood that that if you are mapping any x to any slot, then the probability my hash function, internally it is using h1 h2, that I know. Internally it is using h1 h2 by doing something that I do not need to care about. But what I finally got is that the probability that it is mapping to slot 1 or maybe any slot of your choice, the probability is 1 upon m, which means ultimately I am using a uniform hash function. Ultimately we are using a uniform hash function. Using 2 uniform hash functions, that is fine. Uniform hash function, right? So this is what I want to conclude to everyone. Let me quickly know if that is fine so that I can move to the other explanation that I want to explain you. Okay, cool. So let's just continue from here. Now what I'm saying, that ultimately you are using uniform hash function. Now I can say that if I'm using uniform hash function, then my problem is very simple. If there is a uniform hash function, then I just calculated that for the uniform hash function things are like this, right? For uniform hash function, expected number of keys that map to any slot using uniform hash function is actually n by m, right? This is what I just calculated. So basically my answer is n by m. So here my answer will be B. That's very easy question. I mean, easy, just like the conditional probability that you need to know, that you are essentially using the uniform hash function, right? Okay, let me know if that is clear. So let me just quickly tell you what we are doing. We are, with some probability, we are picking this h1. Now you might say that okay, you are picking this h1 only when it is even, right? Only when it is even. So what do you mean that with some probability you are picking the h1? because in the question they are saying that in with they are not saying that with some probability, they are just saying that if it is even, then only you are picking H1, otherwise you are picking H2. So what is the probability that you are picking H1? I mean, in the question they are saying that only when this X is even, then only you are picking H1. So you are picking H1 only when X is even. It means that this P, like picking H1, is same as that X is even, which means that you are picking H1 only when X is even, which means picking H1 probability, okay, which means P is the probability, is that X is even, okay, probability that X is even, that's the P, right, probability that X is even. So let's suppose N is total keys, and then you will say that whatever the even number of keys, you will say this is the probability, okay, even keys upon total keys, this is the probability by which X is even, or in other words, by which you are picking H1. This is the probability by which you are picking H1, right? Similarly, if they ask you that what is the probability that you are picking H2, then you will say odd keys upon total keys, that will be the probability which is just 1 minus key, 1 minus P, right? With that probability you are picking H2. Let me know if that is fine to everyone. Let me know if there is any doubt. Okay, is this fine? I know it might be a little difficult, but I hope that is fine. Cool. Let me move further. Now, what I want to say is this. Basically, finally, I found out that n upon m is the answer, right? Okay, I hope you understood this. Now, let's just move to the next problem. Yeah, there are a few. So, now let's just solve some linked list PYQs, right? Let's just solve some linked list PYQ. Then we will be solving some stack and queue PYQs. So let's solve this PYQ. What they are saying, that consider a function f. Okay, they are saying that consider a function f, which is like this. Consider function f below, and then they are saying that this function is something like this. Then int okay, this function is defined something like this, which is a recursive function. It seems like, right? They are saying it is a recursive function, which is basically this p next. So let's just see this function little carefully. Let me do one thing. Let me just maybe copy this function on the next page, and let's just see what this function is doing, and then we will just see what are the options that we have, right? Okay, so let's just see what this recursive function is doing here. They are saying that it is returning p equal null, which means it returns true or false, right? This or means or and these operations tell you that it returns either true or false. So this function returns true when p is null, then it will say that this is true, and then it doesn't care, right? Then it doesn't. Or p next is null, p next is null, then also it return true. Or they are saying that that p data is less than equal to p next data. So basically I will come to this. What does this p null? It means empty linked list. Empty linked list. What does this p next null? It means that only one element. So what they're saying is that if there is an empty linked list or there is only one element, then you will be anyway returning to anyway returning true. That's what they are saying, right? I hope that is fine. Now let's just read this question further. So now what they're saying is that p data is less than equal to p next data, and then they're saying p next, f of p next. So what they're saying is that these are just like a base condition, right? So you can say in this recursive definition, these two are just like a base condition, where they are saying either it is an empty linked list or there is just one, then you will return one, or otherwise when you will return one is that just a second. Okay, so you are saying that p data, so this is the main thing. They are saying the p data, which means that if p is pointing some, let's suppose these are the, at least two members in the linked list. If P is pointing here, at least two members are there, then P data, whatever here is that, is less than equal to P next data, which means it is smaller. Let's suppose it is 3, it is 5, it is smaller. If that is smaller, then I'm at least good. I'm saying that I'm good. I'm not saying this will return true. I'm good and I will pass on to the next, which means now I will say that P is here. Okay, now I will pass on to the next. So it must be happening recursively, right? Which means this is 3, this is 5, and then there must be something greater than 5 only, right? Either it ends, that's fine, but if it doesn't end, then there must be greater than 5. So when it returns true, whenever you are having increasing order sequence, right? Increasing order. So you can say that it returns true. These are the base conditions, but ultimately in overall picture you can say that if returns true when, you can say when linked list is sorted, linked list is sorted in increasing order. Right? Let me know if that is fine to everyone. Is this fine? Whatever I'm asking. Okay. So let's just see what is the answer that we have. Now what they are saying is that for a list is empty. So what they are asking is that for a given linked list P, right, the function f returns one if and only if. The function f returns one if and only if. They are asking if and only if, right? The linked list is empty or has exactly one child. So they are saying this is just a base condition they are saying, right? Either empty or just one exactly one element. Either empty or exactly one element. Yeah, for that it will return true, but not if and only if. For other things also it will return true, right? In general, you can say that it is sorted in the non-decreasing or increasing order. Yeah, non-decreasing order, then it will return true. So this is the main thing that we are doing. Now you will say that it is also returning true for empty and exactly one element. Yeah, this is actually a superset of all the things. I mean, it is returning true whenever you are having linked list which is basically arranged in the non-decreasing order. If their linked list is empty, then also it is actually there is nothing. Then I can say this is covering the case. If it is just having one element, then also it is covering the case, right? So this is a very powerful condition which is covering the A also. This B is a superset of A, right? It is covering A because if the linked list is empty, then anyway it is arranged in the non-decreasing order because there is nothing by which you can violate the condition, right? Do you remember that in discrete mathematics that for there exists X is true for empty X, for empty set? Because there is do you remember this, that there exists X is true, if I can remember correctly, then I think that is right, that there exists X is true for empty X, isn't it? So basically if you do not have any counter example, then you will say that yes, there is no counter example, that's why it is true. So basically you will say that this is the list is sorted in the non-decreasing order. This is true even if there is no element or one element. By default it is true basically because there is nothing to counter. So that's why by default this is true, and this is superset. In general you can say if it is non-decreasing, then you will return, right? Okay, I think that is fine. So B is the correct answer here. I do not have the answer here in the slide, but yeah, B is the correct answer. Let's just move to the next question. Let's just see what this question is doing. This question has been asked in GATE 2010. So let's just see what this question is doing and how to solve this question. Now what they are saying is that following C programs or following C function takes a singly linked list as an input program. It modifies list by moving last element to the first. It modifies the list by moving the last element to the front of the list and modify the list. It modifies the list moving the last element to the front of the list and returns the modified list. Okay, so what we are doing, we are basically we are saying moving the last element to the front maybe, and then returns the head of the list, right, the modified list. So that's what we want to do. Now some of the part of the code is blank, right? So they have made it to blank, and then they're asking that what should we fill here. I think it should be easy question. Okay, so let's just do this question, and let me just copy this on the next slide. Yeah, so what they're saying, move to front, this is the linked list name, right? Move to front. Then they're saying that if head is null, or the head of next is null, it means what? That there is only one element or no element, only one element or no element. That's what they're saying, right? In that case, I don't need to do anything. I just return the head. Otherwise, I will do what? I will check if Q is null. Oh, sorry, I will assign Q to be null. So see, at least there are two elements must be there, and then head is pointing here. I will assign Q to be null and P equal to head. So I will say that P is also pointing here. P next is not equal to null. See, what I want to do, I want to modify this particular pointer. If I want to modify this particular pointer, I think you can see this, right? If I want to modify this particular pointer, then one thing I'm sure, I need to move till this point, right? I move this till this point. Basically, if I want to modify this particular pointer, I need a pointer to this particular node. Then I will say P of next. I need a pointer to this particular node. So what I will write in the while loop is basically, I want to traverse till this point. I will not write P equal null. That will be a foolish thing to do. Because let's suppose if I write some while loop which is saying p equal null, right? Let me just tell you. Let me just shift it. Suppose you are writing a while loop that is saying p equal null. Okay, p equal null. Then when the moment you come out of this while loop, the moment or p not equal to null, let's suppose p not equal to null. Okay, the moment you come out of this while loop, it means that this condition must be false. It means p must be null. P is null once you come out this while loop. If you're writing p not equal to null, right? So if you're coming out this while loop, then it will make the, I mean, you can come out only when p is null, right? I mean, that will not be helpful for you, because if p is null, then p is actually storing null after this while loop. P is not storing the pointer to this, right? So if you want the pointer to this, then always write p next not equal to null. Okay, always write p next equal to, next not equal to null. Don't write p is not equal to null. That will be just a useless thing. I mean, if you want the pointer to the last node, then always write p next equal to null, not equal to null. So if p is here, p next is actually null, then only it will be false, right? Anyway, we have covered this already in a great detail. Cool. So let's just move further. Now what they are saying, that they want to have a while loop which is saying that q equal to p, which means that q is initially null and q will be pointing to whatever p is pointing to, and then p equal to p next, which means p will be moved further. So they are moving this p further. That's all. I don't even know why they need this q. Okay, maybe they need this q later. Okay, they need this q later, I think. Okay, so okay, for this point in time they do not need this q, but yeah. So once this while loop is finished, now can anyone tell me where does this p point to and where does this q point to? P must point to the last node, right? Once this while loop is finished, p must point to here and q must point to just before it. Q is pointing to p, and then q is pointing to whatever p is pointing to, and then I advance this q. So that's what we are doing. So q must point here, p must point here, and ultimately what I want this pointer which is p next to point to this. Ultimately what I want this. So let me go to the next page. So now after this while loop, I have something like this. Right? Now what I'm saying here is that after this while loop, p is pointing here, q is pointing here, and head is pointing here, right? So this is what I already have. Now what we want is basically, right, this is after the while loop that we have. Okay, let me just write it here, after while. Now what we want basically is this. We want this pointer to point here, right, ultimately, and then this should be pointing to null. Basically I want to move it right. This should be pointing to null. This pointer should be pointing here, and then I want that, okay, this head should be pointing here. Basically, I mean, this should be the head, this should be the next. okay, no, sorry, I want to move it here. So this should not be pointing to null. Sorry about it. So this should be pointing here. I want this to be pointing to null, right? So that I can say that, yeah, that I have moved it to first. I think now it is fine. This is the first element. This is second, third, yeah. So earlier it was the first one, this second. So now I want to make this first and then second, like that, right? So this is the desired thing that I want. Now let's just see if we can do it using some code. Then what code you think you should be writing to go from this particular initial thing to the desired thing? So from here to here I want to go, right? From this here to here. So let's just check if we can write some code. What you will say? You will say that, okay, then let me try doing it. Maybe you will say, can you set this p next to null? Can you immediately set that to null? What do you think? Will it be a problem? No, right? So maybe you can say, sorry, this was q and this was the p. So you can definitely say, I think you can say q is equal to null, right? This will immediately break this, okay? And then I still have the access to this. I still have the access to this. So I will say that, okay, p next should point to whatever head is pointing to, right? It will start pointing here, and then I will say head should be pointing to whatever it is earlier pointing to. I think, okay, after these two lines I will be having something like this, right? I will be having a I will be having a linked list which is like this. Then I want the head to also point to whatever p is pointing to, because head is basically the starting point. So then I will say head should also point to whatever p is pointing to. So q is equal to null, p next equal to head, and then head equal to p. Okay, these three things: q equal to null, p next equal to, yeah, I think A should be the answer. Let me know if that is fine. Okay, so A is the, oh, okay, just a second. I think there is something that we have missed. Not q. I'm sorry about it. Not q. Q next. Q next should be null, not q, because I want this pointer to be null. So q next should be null. Okay. So that's why which one is the answer? Yeah, D is the answer, right? So that's why D is the answer. Not q. Q next should be null, right? I hope that is clear to everyone. Let me know if that is fine. Yes, Q next should be null. Yeah, I'm glad to see that everyone is giving the correct answer. Okay, okay. Let's just move further because we want to do many of the questions. Now let's solve this question which has been asked in GATE 2021. It seems like that question is tricky, but there is nothing. I mean, I don't find this question as any tricky question or something. So let's just do this question. Just an easy question. Maybe like I will say that such an easy question that I mean, these kind of question I don't prefer to write to give in the AIMT or to in some mock test, some good mock test that if I want to design. Okay, let's just see what this question is doing anyway. This is just an aptitude kind of question. Let's just see what this is doing. I mean, you just need to dry run this code. So let me do one thing. Let me write this code on the next page, and then we will check that what it is doing. So what we are saying is that there is a main function. In this main function, let's just see what we are saying. We have a pointer box E, right? So there is a pointer box E. Pointer means just a small box. Let me know if pointer, does the pointer mean that this is a struct or something? Pointer just means it is a pointer, right? So it could be integer pointer, or it could be of some other type pointer. It is just having a small box which is having address. So box C is basically some pointer. So after this line, just after this line, the first line, what's going to happen in the memory? I'm telling you what's going to happen in the memory. You will get a memory for box C. You will get a memory for head. Head is also a pointer. You will get a memory for head, which is also pointer. You will get a memory for box n, because this is I mean, these are the variables, so that's why I will get a memory for box n. These are the small box. Small box means these are holding the addresses. And then you will get a memory for index. which is 0, right? So after this line, after this line, this particular line, you will be getting these in the memory. Let me know if that is clear to everyone. So after just first line, you will be getting all of this in the memory, right? Okay. So is this fine? Cool. Now let's just see what this code is doing. They are saying box E equal to head, which means box E and head will point to something. So after this line, what we are doing in the memory, I'm talking about, I mean, this all are in the stack of main activation record. I mean, these are the stack which is containing main activation record. So these all variables are in the stack in the main activation record anyway. So now after this line, you will be having a memory. Sorry about it. So after this line, you will be having a memory from the heap, right? So there will be a memory from the heap, which will be having a memory that you have asked is for struct node. Struct node means that is having two, okay, that is having two things, right? Which is having two things. One is value, another one is next pointer. So basically what I'm saying here is that after this line, after this particular line, you will be having something from in the heap. Now there is some box that you have created from the heap, and then you are saying that head box E and head both are pointing to the same thing. Box E and head both are pointing to the same thing, right? So let me go to the next page and let me tell you what is happening with the code. So basically after these two lines, you have something like this. You have, there is a struct that you have, there is box E that you have, right? There is box E which is pointing here. This is box E. There is a head, let me write head here, which is pointing the same thing. And then there is box N also, which I'm not initializing currently, but yeah. So after these two lines, this is what you have as a diagram. Is this diagram clear after these two lines? Right? Now what you are having, head value equal to index. So which means whatever this is pointing to, this is index. What this index value is initially, it is 0. So you will be writing 0 here. And then what you are saying, so you will be writing 0 here. Then you are saying this line is done, this line is done. Then you are saying that let's just run this for loop now, right? Now you are going to run this for loop. Let me know if that is fine. Now we have not run this for loop yet, but yeah, we are going to do it, just an extra. Okay. So let me just do one thing. Let me just remove unnecessary stuff that I already have. Okay. And let's just focus on this for loop, and then we will see what this next for loop is doing. So let's just focus on these two for loops step by step. So this is the first for loop. This is the first for loop. Let's just focus on this, right? So before this for loop in the memory, I have this diagram. So this is how my memory looks like. Now they are saying that box n is also some pointer which is getting allocated. So let me write the box n here, right? Box n, which is now pointing to some struct, right? Which is now pointing that I have taken from the heap. So this is pointing to that these variables, this memory, these memories are from the struct, sorry, from the heap, and these variables are in the stack. These variables are in the stack. I hope that is okay to everyone. I mean, you should be knowing it, right? Okay. So now after this line, so I'm executing the for loop. For, let's suppose I do it step by step, and then let's just remove this. Okay. And let me just do it step by step. So before the for loop, I hope this is clear. So this is before the for loop. Now I'm just going to execute this for loop for step by step, which means for I equal to or index equal to 1, let's just see what is happening in this for loop. So what will happen? You will be having for index equal to 1, you will be executing this box E of next. Box E of next means this pointer. This will start pointing to box N. Box N means whatever box N is pointing to. So this will start pointing here, right? After this line, then box N value, this is the index which is 1, right? And then box E equal to box N. Now box E will start pointing to whatever box N is pointing to, which means that this will start pointing here. This is broken, right? So basically This is after index equal to 1. So as you can see, maybe they're building a linked list, right? They're building a linked list from here to this like that, right? Maybe something like this. So let's just see what is going to happen for index equal to 2. So this was for index equal to 1. Now let's just see what we are doing for index equal to 2, right? So till now this was just index equal to 1. I hope this is fine. Okay. Now let's just see what we are doing for index equal to 2. Again, there is a one box that I'm asking from the heap. This box n now start pointing here, right? So now box n is pointing here, which means it is no more pointing to this, right? Okay, I hope you are understanding. And then you are saying box e of next, which is this, is pointing to whatever box n is pointing to, which means now you are again asking this to point to whatever this is pointing to. Then box n value, which means this value you are doing for index equal to 2, and then box e is start pointing to whatever box n is pointing to. So now box e start pointing here, right? So ultimately box e and box n both are pointing to the same thing. So see here, this is box E, which is also pointing to. So for index equal to 1, okay, what was the story for index equal to 1? Okay, I think I removed it. Anyway, let me just write it. So for index equal to 1, this was the story. See, if we are just having index equal to 1, then this was the story where, so this is just after index equal to 1. Box is pointing here, box n is. This is just after index equal to 1. Now for index equal to 2, the same thing. You just have one more node, right? I mean, for index equal to 1, you have one more node, one node, and box n points here. Similarly, for index equal to 2, you have one more node. Now they are making a linked list. And now let's just see what is going to happen at index equal to 2, index equal to 3, the final iteration of the loop, right? So let's just see what's going to happen for index equal to 3. This was till index equal to 2. Now for index equal to 3, again, I think I will be making a node. I will be asking my box n, okay? I will be asking my box n to point here. Maybe I can write it here only. So I will be asking my box n to point here. And then what will I say? See, I'm asking my box n to point here. Then I will say a box E next equal to box n, which means this will start pointing here. I think they're building a linked list, right? This will start pointing here. And then, so let me write here. Then box n value is index, so I think they will just keep it 3. And then box E will start pointing to whatever box n is pointing to. So ultimately, box E is also pointing to the same thing. So this is what you are doing in this for loop, right? You are just building a linked list. Let me know if that is fine to everyone. Cool. If this is fine, let's just move further. Okay. Let's just move further. Now let's just bring another for loop that you have here, right? So this is the another for loop. Once this for loop finishes, you will be starting this for loop. So now let's just see what this for loop is doing. Basically, you are just building a linked list, and then let's just see what this for loop is doing. So once you have this linked list in place, then we can talk about this for loop. Just a second. Maybe I can move it later here. Yeah. So let's just see what this for loop is doing. So now in this for loop, what they are saying is that they are running this 4 times from 0 to 3, which means they are running it 4 times. Okay. So these were the previous iterations, but ultimately I have this, right? These are the pointers that I have. Now they are running it 4 times. They are saying that value of the index, they are printing basically head value. So for index equal to 0, what they are printing, let's just see. For index equal to 0, what they are printing, head value, which is 0. And then head is moving here, head next, which means head is now pointing here. Head is now pointing here. So this is I'm talking about for index equal to 0. These are the prints. These are the print that we are printing, right? And then head is now pointing here. And then I will say that that head value also I'm printing. So this head value is 1. So basically I will be printing 1 also, right? So 0 and 1 I will be printing two things at this point in time. So what they are doing at index equal to 0 or at any index, they are printing whatever head is pointing to. Then they're moving next, they're printing whatever this is pointing to. Similarly, in this index equal to 1, what they will do? They will print whatever head is pointing to. Then they will move next and then they will print whatever this head next is pointing to, right? So this is the head now. This is the new head. And then they will print whatever head next is pointing to. Similarly, for index equal to 3 or index equal to 2, they will print this 2 and then they will point to whatever this head next is pointing to, which means head will now start pointing here, right? And then they will print this 3 because they are printing this 2, moving and then printing this 3, right? Now let's just see the most crucial one, which is index equal to 3. If index is 3, then what they are doing? They are saying that print this 3. Now head is pointing to whatever this is pointing to, but this is uninitialized. This is like a dangling pointer, right? I do not know what it is pointing to. Now they are saying print the 3. Head should point to whatever this is pointing to, right? So this is actually pointing to some garbage value maybe. So head is pointing here. Now access this using the arrow operator, right? Which means now you just try to dereference it, whatever value here it is, right? But which is basically uninitialized memory. So that's why you will say that because of this, in the last iteration you might get a runtime error, right? So that's the answer. See the options. Upon execution, the program creates a linked list of 5 nodes. No. Upon execution, the program goes to infinite loop. No. It has a missing return. That's fine. It dereference an uninitialized pointer that may result in runtime error, right? So that's why D is the correct answer. Let me know if you got it completely. See, that's very nice. I mean, what you need to do, you just need to execute step by step. So initially, I just told you that what these two lines are doing. So these two lines are basically just creating the memory like this, right? I mean, after these two lines, after the first two lines, you will be having memory will look like this. Memory will basically look like this after these two lines, and then I just say that okay, now memory is actually looking like this after these two lines. Now let's just continue with this for loop. So with this for loop, I have just continued what is happening at index equal to 1, what is happening at index equal to 2, what is happening at index equal to 3. Basically, we are creating a linked list. So first for loop is actually fine. There is not an issue with the first for loop. But when I come to the second for loop, then it is printing it, moving next, and then printing it, right? So if you do keep on doing so, you will print this value, move next in the last iteration, and then try to print it here. So which is a segmentation fault or runtime error. Okay, so that's why I will say that D is the correct answer here. D is the correct answer, right? D is the correct answer. Okay, I hope you understood. Now let's just move to the next question. Cool. So there are many questions that I want to solve today, and I hope that is fine. Like we will be spending some time in solving these questions. So what they are saying, n items are stored in sorted doubly linked list. For a delete operation, a pointer is provided to a record to be deleted. Okay, so they want to have a delete operation. A pointer is provided to the record to be deleted. Okay, for a decrease key operation, so they have the doubly linked list, sorted doubly linked list, right? So n items in sorted. Actually, this question is easy, but anyway, doubly linked list. Okay. Now, what they are saying next is that they are saying that now you have for a decrease key operation, the pointer is provided. Okay. If you want to have a decrease key, then pointer is provided. If you want to delete, the pointer is provided. Okay. So they are having couple of operations. One of the operation is delete. The pointer will be provided, and similarly they are having another operation which is called decrease key, right? So see here, this is called decrease key. There are two operations they just talked about. They are saying that an algorithm performs the following operation on the list in this order. So theta and delete. Okay, so they want to perform delete theta n times and then insert log n times, find log n times, and theta in decrease keys. So insert and find log n times and then theta in decrease keys. So insert you want to do, find you want to do, and these are log n times, I mean at max log n, right? Order of log n means at max you can do it log n times, and this is exactly n, I mean exactly cn if you talk about in terms of constant, but yeah, n times, theta n times, right? Okay. Now tell me, this is what you want to do. If you have n items in sorted doubly linked list, then how much time you will taking to delete one item? So let me go to the next page. Basically, sorted doubly linked list. This is what I have, right? Now, these are the operations that we are performing. Delete, find, okay, delete, insert, find, and then decrease key. These are the operations that we are performing, and then they have said that okay, total operations are also given. So basically, they are saying delete is performed small n times or capital N times, basically, right? Delete is performed n times. This is performed log n times. This is performed log n times. I mean, these are the maximum log n times you can perform. But anyway, let's talk about the worst case. This is performed n time, right? So they are performing these many times. Then I need to find out the cost per operation. If you want to delete one key or cost per key, okay, if you want to delete one key, then in the sorted doubly linked list, if the pointer is provided, then how much time you will be taking? If the pointer is provided, and if you want to delete one doubly linked list of one node, then maybe I think it is easy. If you want to delete it, then maybe you want to set it here and you want to set it here. That you can do in a constant time, right? I think should be done in the constant time. So the cost per key is basically constant here for the delete operation at least, right? Okay. So I hope that is fine. Now let's just move further. Now tell me, if you want to find something, then how much time you will be taking? If you want to find, then you will say, or if you want to insert, you will say that you don't know where this key will lie, right? Because this is a linked list, you cannot do a binary search here. So you will be searching linearly, and then you will get to know, okay, where this key is lying. So order of n time you will be taking just to insert. Similarly, to find, you don't know where this key is lying, you don't have binary search here. So that's why order of n time you will be taking for the find also. For per key. For the decrease, if you want to reduce this key to something else, which means if this is 5 and then now it is become 2 or 3, then you don't know that where you should be plugging in this, right? So in the worst case, you have to scan the whole linked list. So this is again order of n. So these are the costs that I am having per key, right? Only the constant time you will be taking in the first operation. Otherwise you will be taking order of n. Only in the delete you will be taking the order of 1. Now if these are the per key operations, now tell me the total time that you will be taking. So the total is easy, right? So total, you multiply it n log n here also n log n, and then this is n square. So finally n square is your answer. So order of n square time you will be taking here if you want to do all of this, right? So order of n square is the answer. C is the correct answer. Let me know if this is fine or there is some issue. Okay. So I hope this is fine, right? Cool. So this is how we have just finished the linked list. Okay. I think there's a reverse also. Okay. There are more questions than linked list. So let's just do this question, and then we will be just seeing the reverse. Then we will be just finishing the linked list. Then there are many interesting questions related to stack. Okay. So have you seen this question related to stack and queue? Have you seen this question? This is very nice question. We will do some nice analysis on this question. Okay. So this is also related to stack. Similarly, there are some other questions. So let me first finish the linked list completely, and then we will be moving to the other questions probably. Okay. Cool. So let's just see this. Maybe this question is easy. If you want, you can do it. Let me just move to the next question. Let's just do this question. This question is quite interesting, so that's why I want to do it first. Okay. So what they are saying, this question has been asked very recently, And what they are saying is that consider a problem of reversing a singly linked list. So they want to reverse a singly linked list, right? To take an example, given a linked list below. So this linked list below is given, and then they are saying that you want to convert this linked list to the following linked list, which means you want to reverse a linked list, right? Okay. So before I tell you that how much time you will be taking to reverse a linked list, let me just ask you a very simple question. Suppose you have some linked list, something like this. I mean, I've not made the all nodes, but yeah, there will be nodes like this, and then there will be nodes like this. But suppose this is something which is pointing to here, and then this is something which is pointing here, and then previous, current, next. These are the 3 pointers which are given to you. Suppose this is the linked list. This is the kind of structure that is given to you. I just ask you one thing, that you want to go from here to here, which means you want to just point to you want this current to point to the whatever this previous is pointing to. So can you tell me which line of code can do the same job? Okay, if you want to go from just here to here, can you just give me a one line which can make my task from this particular structure to this particular structure? Let me know, and then we will be basically solving this question once you just answer this, because the whole question is just depending on the answer of this very simple question. Yeah, so I think if you want to just point here, then you can just write current of next should be pointing to whatever previous is pointing to, right? Equal to previous. It should be pointing to whatever previous is. So I think this line of code will do it. Now, agent, you want to do the same thing. If you want to reverse it, basically what you want to do, you want to do it. I mean, you want to point it here. You want this to point here, something like this. So basically, you want to do it again and again. So that's all we want to do it. Now, what we will be doing? Okay. So let me just tell you that you have this. Now, what we will be doing? We will be writing the same thing, but in the while loop. I mean, this is just one line. We want to do it, but in the while loop. Okay. So see, I have started with this particular configuration. I'm just asking you, I will come to the question of reversing. I'm just asking you that if you want to just move one pointer, something like this, then what you should be doing. Then you just told me that current next equal to previous will be doing the job that you are asking for, right? Current next equal to previous will be doing the same job that you are asking for. I said, okay, that's great. Now let's just do one thing. Let me just say, or let me just ask that if you want this to also point here, then I mean, I want to put it in the while loop. So for that, what I want to do, I want to basically move my all the pointers, which means from here, I want to go something like this, something like this. Something like this. Can you just help me with the code that can basically go from here to here now? Once you just help me with these 2 steps, I'm done with my reversing. I will just do it repeatedly. Okay, I will tell you the whole code, don't worry, but just help me with this step also. I want this previous to point to, so this is given previous to point to whatever current was pointing to. So I think previous equal to current will do this job. Now I want this next to point to maybe whatever. Okay, let me first fix this current. Maybe I can say this current will point to whatever next was pointing to, and then this next whatever I have is on next. I mean, this is the name of the variable. This is the variable in the struct. Okay, I hope you know, right? Okay, so this next should be pointing to, sorry, next should be pointing to what next is pointing to, right? So next should be pointing to, I want this next to point to whatever next is pointing to. So basically, like in just one step, I did what? I just done a reverse, and then I'm asking you that can you just advance your pointers? So if you just advance your pointer, these pointers will look like this. Let me know if these 2 steps are clear to everyone. So these are just 2 steps. I want to do it repeatedly. So what I will do, I will basically put these 2 steps in a loop, in a loop, I will say, let's just do it repeatedly. I will say, okay, now I want, earlier what I did, I made this current to point here, right? Now again, see, this is just a one iteration of the loop. I will say, let's just current to point to this thing. So just imagine if I put this in a loop, then what's going to happen? Sorry. If I put it in the loop, then you will say that, see, you are going to get something like this. You are going to get, this is just one iteration of the loop. Then the second iteration, from the second iteration, let me just probably copy it. See, you are basically going to say that, see, now if you talk about the second iteration, it will point here, right? So basically this is the beginning of the second iteration. So in each iteration, I do have these two steps. Okay, so this is step 1, this is step 2. Now what will I do? I will just put these steps in a loop. Now this is the first iteration of the loop, this is the second iteration, and in the second iteration I just shown you the first step only. Okay, the first step of the second iteration. So this is the I can say this is the second iteration, and I have just shown you the first step here. Let me know if that is fine to everyone. Okay, so I'm just telling you that how you can reverse. Now what we can do, we can put all of this in a loop, right? So let's just quickly put it, and then you are done with your code also. So let's just quickly put it in the loop. You will say that your step 1 is current next is equal to previous, right? And your step 2 is basically shifting your pointers, which means previous equal to current, I mean shifting the pointers next, right? Current equal to next, and here next next should be next should be pointing to whatever next is pointing. Okay, so I can write it something like this. So these are the two steps, and then I will say, I will just have a while loop, while maybe current is not equal to null. Basically initially this current will be the head, right? And then I'm done with this. Now you can just initialize, you can just say that I think I have the code on the next page. Yeah, so I mean I did the same thing. So basically this is the while loop, this is the step 1, and this next is the step 2. Okay, so actually this is just to make sure that you don't get runtime error, that's why. Otherwise this is just a step 2. Just show you, this is step 1, this is step. Just step 1 is doing what? Step 1 is saying, see, this is what step 1 is saying. Let's suppose this is the linked list that you have, and I will tell you from the beginning, but in the middle, if I say this is previous, this is current, this is next, then step 1 is saying that let this current point to whatever previous is pointing to. Okay, current next point to, let this current next point to whatever previous is pointing to. Then I will just advance my pointer. So once I point here, then I will say that, okay, as in step 2, I will say that, okay, let's just do one thing. Let's just, this is done, and let me just advance my pointers. That's all I will be doing again and again, right? This is what I want to do again and again, and then you are done with your code. That's all, right? See, this is what you're doing. Then again you will say, okay, let me just point here, let this pointer, whatever current next is, let just this pointer point here, and let me just advance my pointers. That's all you need to do to reverse the linked list. These are just 2 steps, right? Now these are just initialization part. I mean, the previous is initially null, current is initially head, and next is initially the head next or current next, right? This is just a small initialization part that you need to take care. And then ultimately your linked list will look like this. Right? And then this current, basically I'm saying current not equal. Okay, I'm saying here current not equal to null means after this while loop, current will be null. I mean, you can come out of the while loop only when current equal to null, right? So if current is here, I mean, if this is null, current is actually here, then previous is here, and next I don't care. And basically the previous is actually pointing to the head of the linked list, so I will be returning the previous if you want to return, otherwise that's fine. right? Let me know if that is fine to everyone. Have you understood this, that how we are reversing the linked list? That's very easy. I mean, there is nothing fancy here. I'm just doing two steps. I'm moving my pointers a little bit. Okay, that's all. Okay, cool. So I hope that is fine. So this is how we can actually reverse the linked list. Now let's just see this question. What this question is asking. Okay, this is saying that given this linked list, you want to have this linked list, which means you should be reversing it. Then which one is true? Okay, and we want to do it in the order of one space. Order of one space means you should not be taking the extra array, extra things you should not be taking. Obviously the linked list will take order of n space. I mean that you anyway have to store, but the space complexity doesn't deal with the input, because input anyway you have to store. So basically apart from this input, I don't think this function requires anything, right? So this function is very simple, right? This function doesn't require anything, any space. So just 2-3 pointers, which is just constant space you will be requiring. So the best algorithm will take theta n time in the worst case. Yeah, in the worst case it will take theta n time. N log n I don't need, right? In the worst case, n square also I don't need. It is not possible to reverse. No, it is possible to reverse in order of one space. So that's why A is the correct answer. Let me know if you have understood this. I mean that is the best explanation that I can think of. Okay. Basically I tried to make it very intuitive. This is just two steps. Every step you just, and every step what you are doing, actually you are just asking it to point. Okay, let's just point here, just move my 3 pointers further, right? That's all you are doing at every step. So this is the most intuitive way that I can explain you, at least. Let me know if you have understood. Okay, so today we talked about like hashing, how the hashing is working in case of uniform hashing. Like I told you, the most mathematical way that is possible, right? Expectation and all, and reversing the linked list. Now, I think there is one last question that I want to do in the linked list, and then we can just solve stack and queue questions tomorrow. And tomorrow, I will try that. Okay, tomorrow class is at 10 a.m. for sure. Okay, don't worry. And I will try if I can conduct the cache session tomorrow only. So basically, there will be at least, I think I need 6 hours in cache, because there are 65 questions. I want you to make sure, I want to make sure that you people are comfortable in all of these type of questions in the cache. So that's why it might take 6 hours. So tomorrow I will try if we can conduct one of the session of the cache. Okay, cool. So let's just see what this question is saying. They are saying that you are running a while loop. Consider the C program format, and then you are running a while loop. Assume that M and N points to the valid null terminated linked list and invocation of join will. So what they are saying, that there is M which is pointing to null terminated linked list. This is a linked list. M is pointing here and N is pointing here. Let's suppose. Okay. So M is pointing here and N is pointing here. These are the 2 pointers which are pointing something like this. Now what this join is doing, let's see. They are saying that node star P, which means there will be a P which will be pointing to whatever N is pointing to. So there will be a P which will point to whatever N is pointing to. Then if P next is not null, so basically tell me, whenever you are out of this while loop, what you will be having? You will be having P next equal to null. Actually opposite of this, then only you can come out of the while loop, right? Whenever this is false, which means opposite of this. So P next equal to null, which means you are advancing, then P will stop here, right? Let me just take this little bit longer. Okay, so basically let's suppose, so after the while loop, you will say that P next equal to null. This should be the true, which means P will point here. Let me know if that is clear, right? After the while loop, what we are doing. Okay. Now, what you need to do, you basically need to see that what they are saying. So P next equal to M. So now they are saying that now this should point to whatever M is pointing to. Okay. So tell me, will this always work? See, that's not an issue. I don't see there is an issue. Let's just see if there can be a null pointer or error, or some null pointer dereference error or not. Okay. So whenever you are accessing next, you should be checking whether it is null or not, right? So see, this next, before accessing this next, I'm not checking it is null or not. So because of just a small reason, it may give you the null pointer exception, right? Why it may give you? Because I'm not checking. Before this I should be checking whether the p is null or not. If p is null, it will give you, and p null is actually a null terminated valid string, valid linked list. So because of just that, if p is null, that's why it can give you the error. So that's why either cause a null pointer dereference or append m to end of the list. So basically B is the correct answer. It may cause null pointer dereference error, because I should be checking before that. I should be checking whether p is not equal to null. I should be checking this. Whenever you access next, you should be making sure that this particular thing is not null. Otherwise it will be null next, and null next is nothing but error, right? Null next is error. Okay. So B is the correct answer here. Let me check. Yeah, B is the correct answer, right? Cool. So now we are still left with, I was not expecting that we will be left with a few questions, but we are still left with very nice questions of stack and queue. Okay. So there are few nice questions. I mean, nice in the sense that these are just aptitude kind of questions. Aptitude means that these questions does not explicitly deal with any particular knowledge, but they just have to deal with some aptitude. I mean, the data structures or the algorithm knowledge is not needed for these questions, whatever they have asked till now, but some aptitude kind of question. So we will be solving it. Otherwise, like if you want, you can solve it. Otherwise I can conduct just one session to solve it. Okay, so all of these kind of questions I have taken, and then this is the question that I have been asked for the queue. For this is again aptitude kind of question. So if you want, honestly, you can also skip these questions. Reason why I'm saying you can skip these questions is because these are just aptitude kind of question, and these concepts, whatever you will do here, might not help you anything in the gate, which means that you will solve it, you will feel happy, which is good. I'm not saying it is not good. What I'm saying that whatever you learn from this question may not be applicable to any other question, because this is just an aptitude question. Okay, so maybe we can just conduct one more session, or otherwise you can also solve, if you want you can skip also, otherwise we can conduct one more session. Most probably we will be conducting one more session just to solve these 4-5 questions. Okay, cool. Thank you everyone. So if there is any doubt, you just comment it out. Otherwise, just in the comment, let me know if you have understood reverse of linked list, if you have understood how does the hashing works, if you have understood that the third largest in BST, that question variation also. Okay, and the variation answer also, just comment it out. Answer of the variation that I talked about, right? Answer of variation. So just let me know if these things are clear to you. Take care. Bye bye. If there is any issue, just you can comment it out. I will be